Alright, learning target 7. Evaluate a quadratic equation in a real-world context and interpret the meaning. Um, so we're just going to go through some quick examples. I'm going to kind of speed through all of the actual solving. Once we get the equations, I'm going to kind of skip through that really quick. By this point, you should know how to solve these anyway, so I don't think that's a problem. Really what the focus of this video is going to be is setting up the equations, and then once you have your answer, actually interpreting what that means, kind of like taking it back to the context of the question. So the first example that you have is the product of two positive consecutive integers is 156. So find the integers. First thing you need is your equations. So this first equation, my two numbers, my two positive consecutive integers are going to be x and y. We know that they're positive consecutive integers, so that's where we get this y equals x plus 1. In other words, one of the numbers equals the other one plus 1. And our second equation comes from the product is 156. So x times y, our two numbers, their product, equals 56. Those are our two equations. Now we have a system. If you go back to last unit, you learned how to solve systems. So we're going to solve this one by substitution. So I'm just going to sub in that y equals x plus 1 for y into the second equation right here. I get x times x plus 1 equals 156. First I expand it. So use distributive property and you get x times x plus x times 1. So x squared plus x equals 156. I want to subtract this 156 from both sides so that I have it in general form. Remember we talked about general form in learning target 2. And then from this point, this is factorable. And if you think about what we talked about in learning target 3, we talked about a good time to factor is when you don't have a coefficient on this x squared. And so we don't have a coefficient here. I mean, it's just 1. So we can go ahead and factor this. So we factor and we get x minus 12 times x plus 13. And so our solutions, we're solving equal to 0. Our solutions for x are x equals 12 and x equals negative 13. Now, go back to the question, because this is what we've done is we've solved it, but the question said the product of two positive consecutive integers. So x equals negative 13 will not be one of our solutions. Okay. We've solved it for x, but we still haven't answered the question quite yet because we want to know both integers. So we know one of them is 12, and then we know y has to be positive 13. Y equals x plus 1. So y equals a positive 13. Your next example, the length of a rectangular pool is 10 meters more than its width. The area of the pool is 875 meters squared, so find the dimensions of the pool. It's going to help you to first look at this drawing. Okay, and I realize now it's really blurry, but my bad, whatever. The dimensions of the pool are x and x plus 10. So if we want to find the area, we multiply both dimensions times each other, okay, like base times width or length times width or however you want to think of it. So x times x plus 10 is going to equal 875. So that's where our equation comes from. Now remember, you can't, while it looks like it's in factored form, since this is not equal to 0, you can't just go ahead and say, oh, x equals 0 and x equals negative 10. Done. Okay. So you actually have to move that, well, first expand it, and then move the 875 over to the other side, so now you have it in general form. Then you can go ahead and factor. So we'll factor and get x plus 35, x minus 25 equals 0. So our two solutions are from solving it are x equals negative 35 and x equals 25. But again, think of it in terms of the problem because you're not done yet. If you did this on a test or something, you would not get full credit because you haven't answered the question. So find the dimensions of the pool. Obviously, you can't have a dimension or you can't have a length of negative 35. So I'm just going to go ahead and cross off that solution. But x can equal 25. So the dimensions of our pool, to finish answering the question, are 25 on one side, and then x plus 10 on the other side. So it's actually going to be 25 by 35. And that's your final answer. You've totally answered the question now, and it makes sense because they have to be positive, whereas our negative 35 made no sense. Our last example then is a projectile motion type problem. So you've got this equation, h equals negative 4.9 t squared plus 16t plus 2.2. And that models the height of a stone thrown into the air. T is seconds that the stone is in the air. And then h is meters. So h stands for the height of the stone in meters. So the first question is, how long is the stone in the air? And we can first look at the graph to kind of get an estimate of how long the stone's in the air. If we look here at the x-intercepts, or the zeros or the roots, we'll see that this is the flight of the stone. So first, it travels up, travels down, hits the ground right here at almost 4 seconds. So when we get our answer, we're going to expect it to be about 4 seconds. But we want to know for sure. So I'm going to plug in 0 for the height. Because obviously at height 0 meters off the ground, that's when it has hit the ground. So I plug in a 0 for h, and then I'm going to solve it for t, because t is time in seconds. So once I've solved this for t, that'll give me how long the stone was in the air. So looking at this equation and thinking about learning target 3, how to determine how to solve this, I mean, you can go ahead and try to factor it, but you're going to hate yourself for doing it. So I would just go ahead and use quadratic formula for this. Identify your a, b, and c, plug them into the quadratic formula, and you should get, obviously you'll get two answers, but one of your answers will be back here at like negative 0.2 seconds or something. Obviously we're only interested in the positive answer. So the positive answer gave us about 3.59 seconds, if you find that as a decimal. So the stone is in the air about 3.59 seconds. And that kind of agrees with what we had estimated from the graph. That looks like it might be about 3.6. So the second question, when was the stone 10 feet above the ground? So we're looking right here and right here. So we're going to have two times that it was 10 feet above the ground. If we kind of estimate using the graph, looks like maybe about slightly less than 1 second and right about 3 seconds. So right about 1 second and 3 seconds are what we should expect to get for our answers. So when is it 10 feet off the ground? I'm going to plug in a 10 for h because I'm interested in a height of 10 meters. These 2 points are where the height is 10 meters. That's what I'm interested in finding. So I'm going to set 10 instead of h. 10 equals negative 4.9 t squared plus 17t plus 2.2. All I've done there is just copy it down. I have to put it into general form though. So I have to set this equal to 0, meaning I have to subtract a 10 from both sides. So this is my new equation. And then obviously my A and B are the same, but C has changed. So I plug those into the quadratic formula, and it gives me two answers. It gives me 0.55 seconds. Okay, so I guess my estimate was a little off, but 0.55 or 0.544 seconds, and x equals 2.93 seconds. So about 3 seconds. So to answer the question, when is the stone 15 feet off the ground? It's 10 feet off the ground. It's 10 feet off the ground after about a half a second and about 3 seconds. The last question, what was the height when the stone was thrown? So what was the original height of the stone? Here at t equals 0 times 0, that represents where it's thrown. So just slightly above 2 meters. And if you remember from our discussion about LT1 and 2 part 2, general form like this gives us the y-intercept. So there's no real calculation you even need to do. You can see from right here, C is the y-intercept, 2.2 is the y-intercept. So that's the original height when it's thrown. You can think of nothing really matters to the left of this y-intercept because that's all just negative time. So about 2.2 feet. Oop, that should be meters. That's my bad. Change that to meters. So about 2.2 meters is how high the stone starts when it's originally thrown. So before class, Susie wants to build a garden that has 3 separate rectangular sections. She wants to fence around the whole garden and between each section as shown. The plot is twice as long as it is wide, and the total area is 200 feet square feet. So how much fencing does Susie need? First, we'll want to find the dimensions of this whole rectangular plot. We can find that because we know that this side is x, this side is 6x, and the total area is 200 feet. So use that to find x. Then you can find how much fencing she will need.